So in this video we're going to look at finding the area of a circle sector. And all a circle sector is what you get when you sweep through some angle theta around a circle where you don't sweep out the entire circle. So this shaded area here is a sector of a full circle. And the basic principle is that we know how to calculate the area of a circle. The area of a full circle is just pi times the square of the radius. So if we have a circle sector, we've only swept through a fraction of the full circle, which means we have a fraction of the area of an entire circle. And what we can do is identify the fraction of the area that we have. So if we're working in degrees, in degree world, we'll do this first. What we want to recognize is that movement through an entire circle is 360 degrees. And if we've only gone through theta of those degrees, then the fraction of the circle that we have is just theta over 360. So the area of the sector is going to equal the fraction of the circle that we have times the area of an entire circle. But the area of an entire circle is just given by pi times the square of the radius. So we get this little formula that doesn't need to be memorized. We just want to recognize the concept is I have the area of a circle and I need to multiply by the fraction of the circle that I'm working with. If we're working in radian world, things actually clean up a lot more nicely. And in radian world, what I want to recognize is that one full rotation is 2 pi radians. So in radian world, if I sweep through theta radians, the fraction of the circle I have is theta over 2 pi. So the area of a sector is just going to equal the fraction of the circle through which I have swept, theta over 2 pi, times the area of a full circle. But the area of a full circle is given by pi r squared. And notice here we get pi divided by pi is 1. And the formula simplifies to division by 2 or multiplication by a half times theta times the square of the radius. And we wind up with a formula for finding the area of a circle sector that doesn't rely on pi, that just relies on your knowing the angle and the radius. The most common mistake that I see students make is replacing theta with an angle in degrees when this formula requires that you're working in radians, because that's what caused the canceling of the pi that does not happen when you're working in degree world. So let's do a simple calculation first, and then we'll follow up on the next slide with an application problem that's a little bit more difficult. So this is what is the area of the sector of a circle that has a radius of 5 and that corresponds to an angle of pi over 4 radians. And just as an aside, in trigonometry, in mathematics in general, if we don't give the angle measure, if we don't tell you whether it's degrees or radians, it's implied that this is in radians. So this is pi over 4 radians. And all we need to do to calculate the area of that sector is to use the formula 1/2 theta r squared. So we get 1/2 theta. Theta is pi over 4 times r squared, or 5 squared. So we get 5 squared is 25 times 1 times pi is 25 pi over 4 times 2 is 8. 25 pi over 8. And we're measuring in feet, so this is going to be square feet. I don't need to have memorized this formula to make this calculation. I can just simply take the approach of finding the fraction of a circle I have. So I could say, look, I've swept through pi over 4 radians. Were I to sweep through an entire circle, I would be sweeping through 2 pi radians. So the fraction of the circle I have is pi over 4 divided by 2 pi times, what's the area of a full circle? Well, it's pi times the square of the radius. And then I could do some simplifying. I could say, hey, pi over 4 divided by 2 pi, division by a number is the same as multiplying by its reciprocal. So This is the same, this complex fraction can be converted into this form, times pi times 5 squared is 25. Pi divided by pi is 1, and we wind up with 25 pi times 1 is 25 pi. 25 pi over 4 times 2 is 8 square feet. So an application problem using the area of a sector of a circle. Here's one. Motion detector can detect movement up to 25 meters away through an angle of 75 degrees. So if I draw that situation, it's going to look like, hey, my motion detector is right here. He can detect motion through a distance of 25 meters and an angle of 75 degrees. So in other words, the motion detector M can detect motion within a circle sector, and we're asked to find the area that can be monitored. So the area of that sector. Here I see that I'm measuring in degrees, so the formula 1/2 theta r squared cannot be used because I'm not working in radians. I would need to convert degrees into radians to use this. But I do know that I have a fraction of a circle. 365 degrees is a full circle, and I have 75 of the 360 degrees is a full circle. 360 degrees is a full circle, and I have 75 out of the 360 degrees. So there's the fraction of the circle I'm working with, times pi times radius squared. So this is the area of a full circle times the fraction of a circle I have. 15 will go into both of these numbers. 15 will go into 75, 5 times? And 15 will go into 30 twice and leave me with a 60. 15 will go into 30 twice, and then 15 will go into 60. Whoa, just had one of those nice hiccups. 4 times. So 24 times 15 should equal 360. And now I can just multiply everything out. 25 squared times 5. If I hammer that on the calculator, I get 3125 times pi over 24. And my measurement was in meters, and this is an area, so this is going to be square meters. So there's the area that the motion detector can detect. And we could pop this into calculator and get well, the word just went out of my head. We can estimate it using the calculator if we needed to. So I'm going to do a follow-up part B on this. If you do estimate it with the calculator, you get 409 square meters. So a follow-up question. So here's a possibility for radius of 25. So in other words, keep the radius the same. Don't change the radius. What angle is required to monitor 50% more area? So we want to recognize that 50% more area would mean we need 150% of what we originally had, or we take the area, here's the area we calculated on the previous slide. To get 50% more area, I would need to multiply this area from the previous slide times 1.5. I need it to be 1.5 times the size it was previously to be 50% more, or as a mixed number, which is probably easier to use, 3/2. So 50% more area, 50% more area than what we previously had on part A, we would get by multiplying 3/2 times the 3125 over 24 pi, and 3 would go into 24 8 times, so we would wind up getting 3125 pi over 2 times 8. And because we're going to be doing some math, I don't want to crunch these numbers out and make them any larger than I have to, so I'm going to leave it in this form. So we know that area, we're looking for a new angle, so we don't know what the new angle is, but we're keeping the radius constant. We're sweeping through a larger angle so that we pick up more area now, square meters, And we're being asked to find this angle that will do it for us. What is this angle? So that angle will be some fraction of the entire circle, so theta over 360. I'm going to use 360 because in the previous slide we were given an angle measure in degrees, so I'm going to stay consistent and keep things in degrees. So here's the fraction of a circle I've swept out, and the area that we want to get, area, we know the formula for area is going to be fraction swept out times pi times the radius squared. The radius is 25. So here's our area calculation for our unknown angle, but we know what area we want here. We want this to be 3125 pi over 2 times 8. And what we would like to recognize to make our life easier is that this 3125 was built on this slide by multiplying 5 times 25 squared. That's where the 3125 came from. So right here I can replace this 3125 with 5 times 25 squared, which is where it came from. And then I can cancel things pretty easily. Divide both sides by pi. Divide both sides by 25 squared. And then we wind up with, if we clean things up a hair, we wind up with 5 up here in the numerator over 2 times 8 equaling theta over 360. Multiply both sides by the 360 to get theta isolated. That's going to be a 1, so this will be our theta. And then we can do some cleaning up here. 2 will go into 36 18 times plus the 0. 2 goes into 2 once. And 4 goes into 8 twice, and 4 goes into 18. It's going to go in 4 times. And then 5, it's going to go in 45 times. So we wind up with 45 times 5, which is, what, 5 times 4, that's 40 is going to be 225. 5 times 45, 225 over a 2. Or if we want to write this as a mixed number, because we're working with an angle, maybe the mixed number is a nicer way to have it. 2 goes in there once, twice into 5 with 1 left over, to 112 and 1/2 degrees is the angle that we would need.